আমি কি শুরু করব? শুনতে পাচ্ছ? শুনতে পাচ্ছ তোমরা? একটু 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 কথা বলো, মাইকে কথা বলো। দেবব্রত,
Yes, sir.
তুমি কে? দেবব্রত,
Yes, sir.
একটু জোরে বলো।
Yes, sir. শুনতে পাচ্ছি।
আরেকবার বলো।
হ্যাঁ স্যার শুনতে পাচ্ছি।
ঠিক আছে, দাঁড়াও আমি একটু আমার মাইকটা আমার বক্সটা চেক করে নিই। দাঁড়াও। ঠিক আছে, আরেকবার বলো, শুনতে পাচ্ছ কিনা?
Yes, sir.
ওকে, থ্যাংক ইউ। আচ্ছা, now in the last class we discussed irrevocable control strategy. In the last class we discussed irrevocable control strategy. Why it was called irrevocable? Do you have any idea? Can you explain? Can any of you explain? Please explain why it is called irrevocable. We already discussed this thing in the last class. I am ready to have even a wrong answer from you, but I need an answer. Hello. Please explain why it is called irrevocable. This part we discussed. in the last class? Kindly explain.
Sir, because we cannot go back to the previous state.
That is, after conducting search up to certain node in the state space graph, if we find,
Sir, we cannot go back to the previous state. So if we encounter any problem, we have to start again from the beginning.
very good, very good. That means we cannot backtrack to an earlier point of decision, to an earlier node of decision, and we cannot have the opportunity to revoke any of our earlier decision on rule application. That is why it is called irrevocable. Once a rule is applied, a state is generated, a path is discovered, that is final. If it happens to provide you, if it happens to lead to the goal state, then it is all right. Otherwise, if you reach the dead end of a path, then you have no option to reconsider, to revoke any of your earlier decision on rule application, so that you can redirect the direction of your search. You can redirect the search. That's why it was called irrevocable. Now, when we work under irrevocable control strategy, what methodology we can follow or we can apply to make the search directed towards the goal, to avoid that search being further away from the goal node. What methodology, what strategy we can adopt to make the search directed towards the goal? Tell me.
Sir, we can use informed strategy. Sir, informed method.
That means we can use hill climbing method.
Yes, sir. Hill climb
If we
procedure.
can design a hill climbing function which will provide maximum functional value when the goal node will be supplied as its argument, the function will provide maximum value, and in all other cases it will provide a less value. In that case, we can apply hill climbing function to choose the direction of search. Now, what are the limitations of hill climbing function? Tell me.
Sir, a flat local maxima can occur.
Yeah, it can stack on local maxima, or the search becomes problematic if there are ridges and plateaus with the hill climbing function. In such cases, we have to select a path randomly to get out of that, but we are not sure even by choosing a path randomly in such cases, in case of local maxima, in case of ridges, in case of plateaus, or whether we will be able to solve the problem, we are not very sure. So these are the major limitations of hill climbing search. Now next I am going to explain backtracking. That is we want to develop algorithm so that we can backtrack on some node over the path which is currently being searched or which is currently being visited, if we find at some node that it will not lead to the goal state, in that case, we want to design the algorithm so that the search will be allowed to backtrack to some earlier node and to reconsider the decision on rule application. So this is called backtracking, and I am going to explain backtracking now. So backtracking is a control strategy for state space search. Under this, we will be allowed to backtrack on a node over the currently explored path if the search direction is found not to be towards a goal. Now let me first explain this with an example. মুছে দিচ্ছি।
স্যার 1 মিনিট দাঁড়িয়ে। স্যার হয়ে গেছে।
তোমরা বোর্ডটা পড়তে পারছো? বোর্ডের লেখাগুলো?
স্যার হ্যাঁ স্যার,
হ্যাঁ
হ্যাঁ স্যার,
আচ্ছা,
স্যার হয়ে গেছে।
হ্যাঁ হ্যাঁ ঠিক আছে, বুঝছি। Now I am trying to explain backtracking with an example. Let this graph represent the state space of a problem. And you should know that all the arcs in this graph are shown with dotted line, because initially no path in this graph has been explored, and initially the entire graph or entire state space is unexplored. And what we do, we actually store these graphs implicitly. That is, we store the start node, we store the goal node, and we store the necessary rule for generating nodes from start nodes and other nodes. And that's why I have shown all the parts in this graph with dotted lines. Now let us try to search this graph to find a path joining start node to a goal node. And from where we will start? Obviously from start node. And when we start from the start node, we compare it with the goal node. And here it fails to match with the goal node. So what we should do? We should generate one successor of the start node, as we did in case of irrevocable control. That whenever we fail to match a state with a goal node, we applied one rule over that node and generated a successor to continue the search. So if A fails to match with G, we will generate a successor of A, that is B. In this case, D also fails to match with G. So we should again visit another successor of D. Now one point that I should mention here, that in case of irrevocable control, I mentioned that we can use depth bound to check whether we are searching in the right direction. And let us assume that depth bound DB, the depth bound here is 1, 2, 3, 4. Let us assume this to be 4. So up to depth 4 in this state space graph, we can continue search. Now what is the depth of node E in this graph? What is the depth of node A in this graph? What is the depth of node A?
0.
Huh?
0.
0. What is the depth of node B in this graph?
1.
What is the depth of node E in this graph?
2.
Okay. Now, again, when we reach node E through this path ABE, it fails to match with the goal node. So we should continue search with a successor of node E. And how can we have a successor of node E? By applying a rule, suitable rule over node E, we can generate its successor, as we learned earlier in case of irrevocable control. Now again, after visiting the node F, it fails to match with the goal node. Now what is the depth of node F in this graph?
0.
Depth of node F.
Acha, F. So 3.
3. So we can continue search beyond node F. And here C is a successor of node F. So we can generate C from F by applying a suitable rule. And again, at this point, C fails to, after visiting node C, we find that it fails to match with the goal node. Now, at this point, what we should do?
Sir, since we have reached the depth bound, we should backtrack.
Yeah. So the depth of C is 4. The depth of C is 4 in this graph. And after C fails to match with the goal node, we cannot generate the successor of C because the depth of C is 4. That means we have reached the depth bound on the currently explored path. So we cannot proceed further on this path. And since we are working under backtracking regime, what we can do? We can backtrack one level up over node C. So to backtrack one level up over node C, where should we return?
Sir, F.
Sorry, F. F is the parent of C. So we should return to F. Now, F has one successor C, and that we have generated, and we have compared it with the goal node. It fails to match with the goal node. So there is no more successor of F to be generated and tested. So what we should do?
Sir, we can again backtrack.
Again backtrack to the parent of F, that is at node E. Now after coming to node E has two successors, one is F and one is C. F has already been generated and tested. C has also been generated and tested. So we should continue backtracking to the parent of E, and that is B. Now after reaching B, we find that B has two successors. One is E, another is G, and we have already generated and tested E, one successor. So after reaching B, what we should do? We should apply a suitable rule on B to generate this node G. And after this node is generated, what we will do, we will compare it with the goal node. And in this case, it exactly matches with the goal node. So, what we will do, we will stop here. And what is the solution? Solution is A, B, G. So this is an illustration for explaining backtracking before Q. Now this illustration is not sufficient for its computer implementation. We need to have an algorithm for this. All right. So now before explaining this algorithm, one point you should know that to backtrack from one node to its parent, what we should do, we should keep records of all the nodes which we have so far visited on the currently discovered path. And when we backtrack one level up, where we should, on which node we should backtrack? The node that we have last visited. Do you agree with me?
Yes, sir.
So we need a last in first out data structure, that is a stack for this purpose. Say for example, here when we visited A, B, E, F and C, we could store all these nodes on a stack A, B, E and C. Now after that, what we should do? We should B from stack top, we should compare it with goal. And it fails to match with the goal, then what we should do? We should check whether depth of C is less than the depth bound. Here, the depth of C is equal to depth bound. So we should no longer store C here. So what we should do, if we find that C has crossed the depth bound, we should pop F from the stack top. And again, we can compare it with the goal node. And here it fails to match with the goal node, and all the successors of F have already been generated. So what we should do? We should again pop one node from the stack top, that is E, and it again fails to match with the goal node. Next time, what we will do? We will pop B from stack top, and it fails to match with the goal node, and depth of B is less than depth bound. And what are the successors of B? Successors of B are E and G. E and G. Out of these two successors, E has already been visited. So we will not consider E, but we will consider G. And to consider G, what we should do? We should push it again over the stack. So by using stack, we can retrieve the node we visited last. So the algorithm that we are going to discuss for implementing backtracking for state space search, it will use a stack as a data structure. Do you agree with me?
Yes, sir.
ও ও আচ্ছা, আমি একটু মুছে লিখছি, এটা আমার অনেকটা স্পেস দরকার, আমি একটু উপর থেকে লিখছি। এইরকম দুটো দুটো স্ল্যাশ সাইনের মানে জানো তো তোমরা?
Sir, comments.
Comments. That is, it is not the main part of the algorithm, but it includes some comments to explain certain statement of this algorithm. অ্যালগোরিদমটা লিখেছো, কপি করেছো?
হ্যাঁ স্যার লিখছি।
লিখে নাও, তারপর বলছি। এক্সপ্লেন করবো?
হ্যাঁ স্যার।
So initially what we will do, we will store the start node on the stack, and initially start node is the only node found on the stack. And to select a node, we will remove it from the stack top. But before removing a node from the stack top, we should be careful about the fact that stack should not be empty, because nothing can be removed from an empty stock, for an empty stack. So if stack is empty, then stop. That means while removing a node from the stack, initially stack will not be empty, because at the beginning we have stored start node over the stack, and it cannot be empty. So this condition will be false. Stack is empty will be false. But when it becomes true, if after visiting all the nodes of a state space graph, if we cannot find the goal node, then the stack will be empty. And under such condition, we should stop and we should print a message that there is no path joining start node to a goal node. And we have visited all nodes joining to start node, but we have not been able to find the goal node. So if we find that stack is empty, then it will stop, but it will print a message that goal node could not be found. Otherwise, a node from the stack top has to be popped. That means remove the node n, remove node n last visited. Remove node n last visited. আচ্ছা, আমি একটুখানি মডিফিকেশন করছি, একটা জায়গায় একটু ভুল হয়েছে। It should not be last visited, but considered last or generated last. Again, So I have do some modification to this algorithm. Please incorporate these modifications. এটা কপি করা হয়েছে?
স্যার হয়ে গেছে।
So after what actually we are doing in this state space search, be it under irrevocable control, be it under backtracking. What we are doing, we are basically every time selecting a node from the state space graph, we are marking it as visited. That is to remember that this node has already been selected. Then we will compare it with the goal node. If it matches with the goal node, our algorithm will terminate. Otherwise, if it fails to match with the goal node, to explore further portion of the state space graph, we will generate one of its successor so that that successor can be next time visited and compared with the goal node. So this is the basic algorithm. And what we are doing, after removing a node from the stack, we should mark that node A visited. And how can we mark it as visited? In diagram, in figure, we can mark it as visited by making it by.
Sir, we can use a set data structure. Sir, we can use a set data structure.
No, we will simply maintain a list. We will simply maintain an array of nodes. Nodes of what? An array of visited nodes. We will copy it into that array. So copy n to a list of visited nodes. So this is equivalent to the operation mark n visited. Then what we will do, we will compare whether n, that is the currently selected node, can be matched with the goal. So we will check it explicitly if n is goal. If n is goal, then search will terminate successfully. So then stop. But if n fails to match with the goal node, what it means? We have to explore further portion of the state space. And to do that, what we should follow? We should generate one successor. There n may have several successors, but out of these successors, we will generate one successor of n. But before, so that successor can be selected and compared with the goal node next time, can be visited and compared with the goal node next time. But before doing that, before generating a successor of the currently selected node n or of the currently visited node n, what we should check? Whether n has reached the depth bound. If n reaches the depth bound, then we will not be allowed to proceed further in that direction by generating a successor of n. But if the depth of n is less than the depth bound, then we will generate a successor of n so that it can be next time visited and compared with the goal node. So if n does not match with the goal node, then what we check first? Whether depth of n equal to the depth bound. If n reaches the depth bound, that means we will no longer be able to generate any successor of n. So what we should do? We should generate other successor of the parent of n. Other successor of the parent of n. And for that, we should pop n from the stack top. Can you follow this step 6?
Yes, sir.
But no one else is answering.
Yes, sir. Understood.
Supro, you are from which discipline?
Sir, production engineering.
Ratul is there. Ratul,
Yes, sir.
can you follow this? Follow this step 6.
Yes, sir.
You are from which discipline?
Sir, mechanical engineering.
Mechanical engineering. Okay, if anyone does not follow this step, please respond so that I can again explain. However, so if n is below the depth bound, if the depth of n is below the depth bound, then we have to generate one successor of n. N may have several successors, and out of these successors, it may so happen that it has already been generated previously. So if it is generated previously, it will be either on the stack or it will be in the list of visited nodes. If it is already generated, we will not consider that successor, we will consider another successor. So this successor of n is a function, it will generate a successor of n one by one, a set of successors. And out of this, we will consider one m. And m should not already be in stack or not yet been generated. Not yet be generated. Then what we will do next time, we have to visit m and we have to compare with the goal node, and for that we should push m over the stack top. So store m on stack to select next, and after that go to step 2. Go to step 2 means again check if the stack is empty. If stack is not empty, then remove a node from the stack top. Which node? That was generated last. And after removing this node from the stack top, first mark it as visited, then compare it with the goal node. If it matches with the goal node, it's all right. Algorithm will terminate successfully. Otherwise, you have to check whether the depth of that node is equal to the depth count. If it is that, then throw away that node, consider its parent by removing another node from the stack top. Otherwise, generate a successor of that node and push that successor over the stack top so that it can be selected next time, visited and compared with the goal node. So this is the algorithm. Now next, I shall illustrate this algorithm with the example of that state space graph which we considered first. আচ্ছা অ্যালগরিদমটা মোটামুটি বোঝা গেছে?
হ্যাঁ স্যার।
আচ্ছা, তাহলে এবার আমি একটা এর ইলাস্ট্রেশন দিয়ে দিই। Let us apply the backtracking algorithm we have discussed on this state space graph to find a path joining start node A to a goal node G. So this is the start node. Initially, what we should do, we should push A on this stack top. In the next step, if we find that the stack is not empty, we will remove one node from the stack top. And it will be compared with the goal node. It fails to match with the goal node. So it will be marked as visited and it will be saved into a list of visited nodes. Then we will check depth of A, whether it is less than depth bound. In this case, it is less than depth bound. So what we will do? We will generate the successors of A. We will generate successors of A. What are successors of A? B and D. And we find that neither of B and D has already been visited or not, neither of B or D have already been generated. So what we will do? Before generating the successors, we have to push. If depth bound of A is less than, if depth of A is less than depth bound, we should push it again on the stack, and then we will generate successor of A, which is B and D. Now out of B and D, let us select one arbitrarily, and as soon as we select one arbitrarily, it will be stored on the stack. And so this is the currently explored path. After that, what we will do, the algorithm will go to step 2, and after returning to step 2, it will check the stack whether it is empty, and in this case it is not empty, so it will remove a node from the stack top. That is the node which was generated last. It is stored on the stack top, and it will be removed from the stack top so that it can be visited and compared with the goal node next. Now this B will be marked as visited. Now we will check the depth of B. Less than depth bound. So what we should do? We should push B on the stack top so that
we can get the successors of B.
So we will store it on the stack top A, B. And after that we will compute the successor of node B. What are the successor of node B?
E and G.
E and
G.
E and G. Out of these two, let us arbitrarily select the leftmost one, that is E. So as soon as we select E, so the currently explored path will look like this. And we should store explode this E on the stack top. Do you agree up to this?
Yes, sir.
আচ্ছা, এবার এদিকে ছবিটা মুছে বাকি অংশটা করছি। জায়গা নেই, এদিকে করতে হবে। তোমরা ছবিগুলো আঁকছো তো?
হ্যাঁ স্যার।
আচ্ছা। So next time, what the algorithm will do? It will go to step 2, and after returning to step 2, it will first check if the stack is empty. Here stack is not empty, so it will remove a node from the stack top, so that that node can be visited and compared with the goal node next. And this node is not equal to goal node. And what is the depth of E? It is less than depth bound. So it should again be stored over the stack top, and the currently explored path will look like this: A, B, then E. Next, we will compute the successor of E. Successors of E include A, B. This is again a successor of E. B, A, and C. Now, out of these two successors, B is already in the stack. That means it has already been visited. So we will not consider B. And out of F and C, let us consider F arbitrary. Now after F is considered, it should be pushed over the stack top. And this will be the currently explored path. And after this, the algorithm will go back to step 2. And in step 2, it will first check whether the stack is empty. And in this case, we find that the stack is not empty. So one node will be removed from the stack top so that it can be visited and it can be compared with the goal node next. Next, we will compute the depth of this node F. We will compute depth of F, and it is 1, 2, 3. So it is less than depth count. And since it is less than depth count, we will again push it on the stack top so that its other children can be selected next. We will push it on the stack top. And what we will do, we will compute the successors of A. What are the successors of A?
E and C.
Successors of A include E and C. Now, out of these two successors, E has already been visited, and it is already in the stack. So we will not consider E, but we will consider C as a successor of A. And after that, the C. So after that, we will push C over the stack top. Now the algorithm will follow the step 2. In step 2, it checks if the stack is empty. Here we find that the stack is not empty. So what the algorithm will do? It will remove one element from the stack top. So C will be removed from the stack top, and it will be first marked as visited, then it will be compared with the goal node. It fails to match with the goal node. So now after that, the depth of C should be computed. Depth of C is equal to 4 here. It is equal to 1, 2, 3, 4, and that is exactly equal to the depth bound we have set. So we cannot continue search anymore after this node C. So we will no longer push it over the stack. Instead, we will pop an element from the stack so that the parent of the C can be considered next. this time F will be removed from the stack top because it has reached the depth bound. Now we will consider the successor of L. This will no longer be compared with the goal node because it has been removed from the stack top because its child has reached the depth bound. So it was pushed over the stack top as the father of this child and it was already visited. So it will no longer be visited. Instead of that, we will compute the successor of this node. What are the successors? So successors of F are E and C here. E and C here. Out of these two successors, E is already on the stack. That means it has already been visited. So we will not consider E because it has already been considered. So and again the C has also been visited not as a child of E but as a child of F. So we will not consider C also. So finally it will look like this. So all the successors of F has already been visited. So we will no longer push X on the stack, and this algorithm will go to step 2 where it will again pop the top element of the stack. So A, E will be popped from the stack top and it does not match with the goal load. So next time what we will do, we will compute the successors of E. We will compute the successors of E. Now before that we will compute the depth of E. Depth of E is less than depth of depth of E. So we will compute the successor of E. Successors of E are B, F and C. B, F and C. And out of this, B has already been visited, F has already been visited, and C has already been visited. So we will no longer push C over E over the stack top. One point. Has C been visited already? Has C been visited? I do not have the portion of the diagram that
Yes, sir. C was visited.
he has the successor of E.
Yes, sir.
So we will not consider C. That means all
So we
the
will again backtrack to B.
but according to which step of the algorithm that I should follow? So it will go to step 2. It will no longer push E or B or F or C. So at this moment, the list of the currently visited nodes will look like this: A, F, B, and B is not equal to goal, and depth of B is less than depth of. So we should compute the successor of B. What are the successors of B? A and G. All right. A, E and G. Sorry. A, E and G. Now A has already been, it is already in the stack. E was previously visited, it is in the visited list, but G has not yet been visited. So what we should do? We should push G over the stack top, and G should be added as a child of B. But G has not yet been visited. Next time, what will happen? We
So
will,
G will be equal to goal.
huh?
G will be equal to goal.
No, we should follow the step of the algorithm.
Yes, sir. We should
Here
pop
can
G.
observe through our eyes, but computer cannot observe in this way. It will observe through by executing the steps of operation of the algorithm.
Yes, sir. So then we should pop G.
So G will be popped from the stack top and it is equal to gold, and so this will be A, B, and G. So here the algorithm will stop. Right?
Yes, sir.
So if you follow this algorithm, then the nodes will be nodes of this state space graph will be visited in this fashion. That I mentioned at the beginning. ঠিক আছে?
Yes, sir.
আচ্ছা। Next point is this: what should be the time and space complexity of this algorithm? Or what should be the order of time and space complexity of this backtracking search? And obviously we are
Sir, time
considering
complexity will be O of all the nodes in the graph.
that is the depth bound. So this will be big O of D. That is the D is the goal estimated goal depth. Or depth bound. Agreed. Because this will be the sorry, this is not the time complexity.
Sir, space complexity O of D হবে.
Sorry. So this will be the space complexity. That is, at the worst case situation, the algorithm has to provide space of length D. That means it has to provide a space that can store D elements there, or D plus 1 elements, right?
Yes, sir.
So it is big O of D space complexity. But what about the time complexity?
Sir, it will be O of number of nodes.
Big O. Big O notation I explained earlier. That is
Yes,
the
sir.
asymptotic complexity.
Yes, sir.
Now let us assume B be the average branching factor of a node in the state space graph. Now in this state space graph, a node may have no children, a node may have two child, a node may have one child, a node may have different numbers of children. Now we are considering B be the average branching factor of a node. That is on average, if A be a node, it will have B successors, B number of successors. Now with this, we will compute the time complexity of this algorithm. That is the worst case time complexity. Now you tell me when the worst case will happen for this backtracking search.
Sir, when we have to visit all the nodes.
Right, when we have to visit all the nodes. So so what will be the estimate for all those nodes? Now we will begin from the start node. Start node. Then it has B number of successors, and we have to visit all these successors. And for each of these successors, we have to again visit the number of successors. So for each of these nodes, we need to visit the number of successors. And for all these nodes, we have to visit the square successors. That is, the depth is 2. Now in this way, when the depth will be d, we have to visit b to the power d number of successors at the worst case. So this time complexity will be big O of b to the power d for this backtracking search. Would you agree with me? For each of these nodes, you have to visit b number of successors, and there are.
স্যার বাট যদি আমি একটা নোট ভিজিট করি সেটা তো আমি আর ভিজিট করছি না।
না করছো না, একটা করলেও তো একটা ওয়ার্স্ট কেস সব নোডগুলো ভিজিট করতে হবে।
হ্যাঁ স্যার,
করতে হবে তো।
হ্যাঁ স্যার।
সেই সংখ্যাটা কত? সেই সংখ্যাটা যদি অ্যাভারেজ ব্রাঞ্চিং ফ্যাক্টর যদি বি হয়, তাহলে প্রথমটার জন্য স্টার্ট নোডের পরে বি নাম্বার অফ সাকসেসরস তুমি ভিজিট করলে, তারপরে এই প্রত্যেকটা সাকসেসরের জন্য বি নাম্বার অফ সাকসেসরস ভিজিট করতে হবে। তাহলে এই লেভেলে গিয়ে গ্রাফের লেভেল 2 তে গিয়ে তোমাকে বি স্কয়ার নাম্বার অফ নোডস ভিজিট করতে হবে।
হ্যাঁ স্যার। স্যার কিন্তু এটা তো ও অফ এন হওয়ার কথা না?
হ্যাঁ,
কারণ ও অফ নাম্বার অফ নোডস হওয়ার কথা ইন দা গ্রাফ।
কি বলছো? তার মানে আমাদের ভিজিট করতে হচ্ছে প্রথমে বি, তারপরে বি স্কয়ার, তারপরে বি কিউব, তারপরে বি টু দি পাওয়ার ডি, তাই তো?
হ্যাঁ স্যার।
এগ্রিড?
ইয়েস স্যার।
দেখো লেভেল 0 তে বি টু দি পাওয়ার 0, লেভেল 0 তে, লেভেল 1 এ b number of nodes, level 2 তে b square number of nodes. Would you agree with me?
Yes sir.
Then this forms a geometric progression,
Yes sir.
isn't it?
Yes sir.
So what will be the sum of this? It will be proportional to b to the power d. Hello?
Sir.
Respond please.
Sir, in case of b to the power d, sir, I don't.
জোরে বলো, শুনতে পাচ্ছি না। বলো।
স্যার বি টু দ্য পাওয়ার ডি কি করে হবে এটা?
তুমি এই সামটা কত হবে বলো না, সামটা বলো।
স্যার কিন্তু আমাদেরকে তো ওরকম করে ইয়ে করলে হবে না।
কিছু শুনতে পাচ্ছি না, একটু জোরে বলো বাবা, আমার বলো বলো। হ্যালো।
ইয়েস স্যার।
হ্যাঁ বলো।
কিন্তু এইভাবে তো ক্যালকুলেট করলে হবে না, কারণ আমাদের ওয়ার্স্ট কেসে তো পুরো গ্রাফটাকে আমাদেরকে ট্রাভার্স করতে হবে।
হ্যাঁ,
তো সেই ক্ষেত্রে তো আমাদের ও অফ এন হওয়া উচিত, আমাদের তো এইভাবে ক্যালকুলেট করাটা উচিত না।
না 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 না, কথাটা শোনো, গেমটা কি?
স্যার এনটা হচ্ছে নাম্বার অফ নোডস ইন দ্য স্টেট স্পেস গ্রাফ।
এক্স্যাক্টলি, সেই নাম্বার অফ নোডস এর এক্সাক্ট ভ্যালুটা কত হবে? The more will be the depth of the state space graph, the higher will be the number of nodes there.
ইয়েস স্যার।
Okay?
Yes,
So
sir.
if the state space graph is of depth 0, how many nodes will be there? Only one node will be there.
ইয়েস স্যার।
If the state space graph is of maximum depth 1 with average branching factor b, then how many nodes will be there? B to the power 0 at the 0th level and 1th level plus b.
ইয়েস স্যার।
If the state space graph has a maximum depth 2, then what will be the total number of nodes there? B, 1 plus b plus b squared.
ইয়েস স্যার।
So this amount of nodes one has to visit at the worst case.
ইয়েস স্যার।
So the time required to search this state space, this will be proportional to this AP series. So to this
Yes, sir.
geometric progression.
ইয়েস স্যার।
And the sum is, what is the exact sum? Tell me. I cannot recollect that formula. কি মনে আছে না নেই? বুঝলে বাবা, তুমি কোনো সারাও দেয় না। হ্যাঁ? হ্যালো? বুঝতে পারছি না, বলো।
Sum of GP series করলেই হবে a into r to the power n minus 1 by r minus 1.
হ্যাঁ, a into, হ্যাঁ রাইট, a into r to the power n minus 1 by r minus 1. So r is common ratio and a is the first term. Right?
ইয়েস স্যার।
Yes, sir. Yes, sir.
So here this sum will be equal to b to the power 0 means 1 and common ratio is b. It is b to the power d, b to the power b minus 1 by b minus 1. Okay? Right?
হ্যাঁ স্যার।
So we are interested about asymptotic complexity. We are not interested about the exact complexity of this algorithm. So the time complexity will be bO of b to the power d. Do you agree?
ইয়েস স্যার, এগ্রি।
So again this is the problem. This is the problem with backtracking search. you agree with this statement? The major problem of backtracking applied for state space graph, this is the major problem. That is, the time complexity is of exponential order. It grows exponentially high with increasing values of the goal depth. And that is, there is a good chance of combinatorial explosion with a small increase of the value of estimated goal depth. Combinatorial explosion, I explained it earlier with that example of Tower of Hanoi with 64 discs. It will require inordinate amount of time, for which we cannot allow a practical machine to learn. Sorry, a practical machine to run. তোমরা আমার সাথে একমত হলে কি?
Yes, sir.
Yes, sir.
So this is why we are studying AI. This is why we are studying AI. The state space search under backtracking control, what it can do, given the state space of a problem, given the rules for generating states from a given state, given the goal state, given the start state, we can run the algorithm for state space search for any problem and we will get the solution.
Yes, sir.
Now, it is theoretically possible because such algorithm that allows backtracking, its time complexity is big O of b to the power d. So there is a good chance of combinatorial explosion for a small increase of goal depth. So we cannot apply this for practical purposes. And AI provides us a way out, because AI teaches us how we can utilize knowledge to do some work intelligently, to do this search intelligently, so that this search can be guided, focused towards the goal. So here comes the role of AI, and how this can be, how we can use knowledge for this, that I shall explain later. We have already discussed hill climbing method. But,
Yes, sir.
but that is not a sound method. It has various limitations. So we need some more sophisticated methods. But before discussing how to make search intelligent further, we should discuss another control strategy that I mentioned earlier, that is graph search control. এটা মুছে দিচ্ছি। So we are discussing control regimes for state space search, and we have already discussed irrevocable control regime. then we started to discuss tentative control regime. And under tentative control regime, we have already discussed backtracking. Next day, we will discuss graph search control. ঠিক আছে? হ্যালো,
হ্যাঁ স্যার।
আচ্ছা কালকে আমাদের ক্লাস হবে তাহলে কটায়? বিকেল 5টায় হোক।
ঠিক আছে স্যার।
হ্যাঁ কালকে বিকেল 5টায় লিঙ্ক পাঠিয়ে দেবো। তাহলে এতদূর হয়ে গেল তো?
হ্যাঁ স্যার।
এবার গ্রাফ সার্চ কন্ট্রোলটা পড়াবো। গ্রাফ সার্চ কন্ট্রোল পড়ানোর পরে আমি দেখাবো how we can conduct search intelligently, how we can conduct knowledge driven search, how we can conduct intelligent search over the state space of a problem. ঠিক আছে?
হ্যাঁ স্যার।
Thank you. The next class will be tomorrow at about at 5 p.m. আচ্ছা আমি লিভ করে যাচ্ছি।
ঠিক আছে স্যার।
ওকে স্যার